All right, so now we're going to discuss energy diagrams. And I want you to understand something. There's nothing new here. It's just conservation of mechanical energy in a picture. So here, this is mechanical energy. Mechanical energy equals K plus U. And if it's conserved, this is constant. And so these energy diagrams, they're situations where this is constant. So mechanical energy is conserved. So just a picture, right? Whoopee! I mean, sorry. But I know that the author, Randy Knight, loves these things, okay? All right. So the first one that we're going to look at is just free fall. So we're just dropping a ball, you know. And so here's y2 and here's y1. And we're dropping it from someplace a little bit higher than y2, okay? All right. So here's mechanical energy. Mechanical energy equals K plus U. And it's U gravity, right? So this is constant, right? Because this is the energy, right? This is the energy and this is the height, right? So this is constant. And then we know that the gravitational potential energy is mgy or mgh or whatever you want to call it, right? So potential energy mgy. Well, you know, it's a straight line, right? M and G are constant, Y is the variable, so it's a straight line. So there it is. Whoop. Okay? So potential energy at 0, you know, at Y equals 0 is 0, no kidding, right? Then it just keeps going up, okay? All right, so this is where you drop it. When you drop it, the kinetic energy is 0, so all of the energy is potential. Bang, right there, right? So the potential energy equals the mechanical energy. And then, you know, then you drop it, right, and then the potential energy gets smaller and smaller and smaller and smaller and smaller. So this is the potential energy at y2, this is the potential energy at y1. So there you go. All right, now, how do you find the kinetic energy from this, you know, from the graph? Well, you know, again, that's the formula, right? So solve for K. So K is just E mechanical minus U. So here's E mechanical, here's U. So you take this minus that, and you get that, right? Or this minus that, and you get that. So that's the kinetic energy at each point. And you got to admit, this makes sense, right? Because E is K plus U. So this E is K plus U. E is K plus U. Ta-da! So that's really, that's all there is to it, you know. Now there's other ways of drawing these energy diagrams. So, wow, okay, so now we're going to throw the ball up. Okay, we're going to throw the ball up from the ground. So you see here, so we're throwing the ball up from the ground. So initially, here it is, right? So this is the mechanical energy. It's constant, right? Here's the constant, and here's the potential energy. So the potential energy at y equals 0 is 0. Ta-da, right? So if this is the mechanical energy, this is the potential energy, this is the kinetic energy. And so here's the bar chart. Right at the beginning, we're throwing it up with some velocity VA. So at the beginning, there's no gravitational potential energy. It's all kinetic, all kinetic. Then we're at some height VB, you know. We're at a height YB with velocity VB. And so here's YB. Again, the energy is constant, so, you know, there's the total energy or the mechanical energy. Here's the gravitational energy. So this is the gravitational energy. This is the kinetic energy. And it's supposed to be roughly half and half. So you can see that some of that kinetic energy has become potential energy, right? Kinetic goes to potential, so they're like roughly half and half. And then we're at the turning point, right? So that means that the ball has stopped. So the kinetic energy, so there's no kinetic energy. So the total mechanical energy is equal to the potential energy, right? There's no kinetic. turning point. We talked about that a long time ago. So there's no kinetic energy, it's all potential energy. And then we reverse, so we're coming back down again. So now we're at some YD, so the mechanical energy, again, is constant, you know. There's the potential, there's the kinetic, so it's roughly 50-50. So there you go. So this is called a bar chart. This is, I don't know what this is called, just the energy diagram, okay? So, I mean, again, it's nothing new, it's just that, but, okay. Now, so that's free fall, right? That's free fall, where for free fall, we know that U is mgy or mg height or whatever you want to call it, okay? So that's free fall. Now, let's do spring. Let's do a spring. So now, for spring, 1/2 kx squared is the potential energy. And what's that? If we were to plot energy versus x, that's a parabola, right? Concave up parabola. Okay, so there we go, right? 1/2 kx squared, nice parabola. Now, there's something you have to realize, though. In order for this to make any sense, so this is the equilibrium length, right? That's if you just put the spring on the table and you don't pull it or you don't push it, you just put it there. So in other words, this is how, that's where the spring would be, right, at x equals 0. But that's kind of ridiculous because it's not going to do anything. If you want it to oscillate back and forth, you have to push it or pull it. So what we're going to always do, we're going to always pull it to x equals a. A is like, A stands for amplitude. We're going to pull it to x equals a, and what's it going to do? It's going to go back and forth, back and forth, back and forth, okay? So you can see then, you know, if I pull the spring to x equals a, it has a lot of potential energy, right? It's not moving, but it has a lot of energy because I pulled it. And so here's the mechanical energy. It's constant, right? So at x equals a, I'm holding it still. So all of the energy is potential. Then I let go, and what happens? Faster, 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 and then slower, 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 stop, then reverse. Faster, faster, faster. This is where it's going the fastest, then slower, slower, slower. So you can see at x equals 0, you know, that's where the spring, it's not stretched, it's not compressed. So there's no potential energy. Right there, no potential energy. So it's all kinetic, right? This has to be kinetic. So, here. Oh, sorry. Okay, so kind of like what we did before, right? So this is potential energy, this is kinetic energy. So U plus K equals mechanical, which is constant, right? And again, this shows that the fastest it's going is right at x equals 0 when there's no potential energy. Now, if you really wanted to go berserk over these diagrams, I mean, you could plot K and U. So here's my U, this nice parabola, right there. Then you could just plot K. So it's 0, then it gets bigger, 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 then at max, then smaller, 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 right? So here's the K. Starts out at 0, bigger, 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 maximum, smaller, smaller, smaller. Okay, so there you go. So again, all it is a graphical way or a pictorial way of showing this. That's all it is. And you can do it, and you can, just like with free fall, you can have two methods of doing this. Okay, I already explained this. I'm not going to explain that again. I already explained this. So let's go to this. Okay, so here, so that's x equals 0, or the equilibrium point. I pull it here to the amplitude. It has no kinetic energy, all potential, right? No kinetic, all potential. Then I let go. It starts moving to the left. So the potential energy is getting smaller. The kinetic energy is getting bigger, right? So here's the potential energy. Here's kinetic. Potential, kinetic. Then I get right here. That's the equilibrium length, so it's not compressed, it's not stretched, there's no potential energy at all. So all of the mechanical energy is kinetic. So you can see the potential is 0. I mean, so this is all kinetic. And again, you know, just notice that the mechanical energy is always constant, right? Always constant. So here at the equilibrium position, no potential energy, all kinetic. Then here, now it starts slowing down because you're compressing the spring. So you get a little bit of potential energy, a lot of kinetic. So there you go. So you should be able to, understand what's going on physically just by looking at these graphs. Okay, let's continue. All right, now here are some, this is a potential energy graph, right? Potential energy versus X. And this is just some generalized potential energy. I have no idea, what it's supposed to describe. I don't really care. It's just some crazy potential energy graph that we're going to discuss, okay? We don't care what it means or whatever. Okay, so let's say we have a particle and it has mechanical energy 1.5 joules, all right? 1.5 joules. Now, here's the question for you, and it's going this direction, let's say. Where does the particle speed up? Now remember, this is mechanical energy. This is potential energy, right? And so where's the kinetic energy? This is the kinetic energy, agree? So where does the particle speed up? In other words, where does the kinetic energy increase? Well, here, the potential energy equals the mechanical energy. So the kinetic energy is 0. But you see here, the kinetic energy is getting bigger, 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 right? So it's getting faster from, let's say, x equals, 0.75 to x equals 1, right? So bigger, bigger, bigger. Here, kinetic energy gets smaller, so it's slowing down. Here, kinetic energy gets bigger, speeding up. Here, kinetic energy gets smaller, slowing down. Where is the speed the greatest? Well, where's the kinetic energy the greatest? At x equals 1 and at x equals 3, right? Because this is all kinetic, right? The potential energy is 0 here, so all of the energy is just kinetic energy. Turning points. Where does it turn around? In other words, where does it stop and turn around? Or here, right? Kinetic energy is 0 there. Kinetic energy is 0 there. So it just stops and turns around. Okay. Are there any forbidden regions? Are there any forbidden regions? Think about that. Okay, in other words, could the particle exist at x equals 1/2? What do you think? So let's say, so x equals 0.5 meters. Is that possible? Well, we have E equals K plus U, right? And so K equals E minus U. Now look, though. Right here, at x equals 1/2, the E is 1.5. But what's U? Well, U is something like, let's say 2.5. So 1.5 minus 2.5 is minus 1 joule. Now, kinetic energy is 1/2 mv squared. How can that be positive? Negative. This is, right? You can't have negative kinetic energy. This is always going to be positive. So in other words, it's ridiculous. It's impossible. So the forbidden regions are, the particle cannot be located to the left of here, right? Which is, 0.75 or something like that. Can't be over here. Can't be over here. Because you'd have to have negative kinetic energy, which is ridiculous. Can't have negative kinetic energy. Okay, now what energy transformations are occurring? Well, potential energy is being transformed to kinetic, and kinetic is being transformed to potential, just like we've seen before. All right, so hopefully that makes sense. Let's do another one. All right, now let's say that the mechanical energy is 1/2 joule. 1/2 joule. And we want to consider the particle at x equals 1 meter, right? So right there. So x equals 1 meter, So the potential energy is 0, so the kinetic energy is half a joule, right? Now, let's just say we disturb the object just a little bit, just a little bit, all right? So we give it just a little more kinetic energy, just a little bit. So what's going to happen when the particle moves away from x equals 1 meter? All right, so it's going to either go this way, well, I mean this way or this way, right? But what's happening when it goes this way, what's happening to the kinetic energy? It's getting smaller. What happens if it goes this way? The kinetic energy is still getting smaller, right? So the kinetic energy is getting smaller, and the potential energy is getting bigger, right? And the potential energy is going to keep getting bigger until the thing stops, right? When the kinetic energy is 0, the thing stops. So so then it's going to stop, and it's going to go back, all right? So it's really going like this, okay? So we're just going to keep going back and forth, back and forth, back and forth, okay? So that's a turning point. That's a turning point. It's just going to keep going back and forth, back and forth. Now, we give that a name. That's called stable equilibrium. And here's the analogy. So here you have a bowl. You have a marble on the bottom. You just give it a little tiny flick. What's it going to do? It's going to go back and forth, back and forth, back and forth, right? So in other words, it's going to go back to where it originally was, right? It's just going to oscillate around that point where it originally was before you gave it a flick. Okay? All right, we're going to use this, believe it or not. All right, so this is a stable equilibrium point, x equals 1. Where's another one? X equals 3 meters, right? So these are both stable equilibrium points, x equals 1 meter and x equals 3 meters. Okay, now let's do another one. Okay, now we're going to say that the mechanical energy is 1 joule. And we want to consider the point at x equals 2 meters. So at x equals 2 meters, you can see that the potential energy equals the total energy. So the kinetic energy is 0, right? Okay, now we're going to give it a flick, just a little tiny, right? Just increase the kinetic energy a little bit, all right? So then the particle's going to move away, either this way or this way. So if it goes this way, what's going to happen to the kinetic energy? Well, bigger, 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 bigger. If you hit it that way, what's going to happen? Kinetic energy is getting bigger, 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 right? Okay, so the kinetic energy is going to get larger and larger and larger. What's going to happen to the potential energy? Smaller, 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 right? So what's going to happen? It's going to move away from the x equals 2, and it's never going to come back, right? It's never going to come back. So what do we call that? I mean, we call the other one stable equilibrium. So it stands to reason that this is going to be called unstable equilibrium. And the analogy here is you take the bowl, flip it upside down, balance the marble on the top of the bowl carefully, right? Then just give it a little flick. Is it ever going to come back to the top? No. No, it won't. All right, so that's called unstable equilibrium. All right, now, I didn't tell you the whole story, but that's okay. I'll tell you the whole story eventually, right? Okay, so this is a stable equilibrium point, right? Now, I said that we had the object at x equals 1 meter, and then we give it a little flick, right? And let's say it moves this way. So if it moves this way, the potential energy increases, the kinetic energy decreases. It gets to that point where the kinetic energy is 0, right? Now, why doesn't it just stay there? I mean, I said it oscillates back and forth. I didn't explain why, because I'm going to do it now. But, why doesn't it just stay there? Well, it's kind of like this. If I throw this up, why doesn't it just stay? Try that again, huh? Why doesn't it just stay at the top? How come it comes back down? Well, it's sort of obvious. Gravity, right? There's a force on it, right? If there were no force on it when it reached the top, it would just stay put. But there is a force on it. It's the force of gravity. And again, we call that a turning point. So maybe there's a force on the object. Huh? Maybe the force causes it to oscillate back and forth, back and forth. Well, let's see, all right? So I'm just going to do like a one-dimensional simple derivation. But the result is generally true. Okay, so for one-dimensional motion, work equals F delta x, right? That's just one-dimensional motion, But we also learned that the work equals minus delta u, right? That was a big deal. Remember, we used that because we don't know how to calculate this from first principles, but we can calculate the work, piece of cake. So that's, remember we did that for gravity and also for the spring, you know. This is super important. Okay, so let's do a little substitution. Let's substitute minus u here, or delta u. So we have minus delta u equals fx delta x. Well, let's divide both sides by delta x. Okay, now let's take the limit as delta x goes to 0. That's a derivative, right? So now you take the limit, delta x goes to 0, you get minus du dx equals to f. Okay? All right. So, ta-da, all right? So that's a big deal, and here's why it's a big deal. So let's say we have the particle at x equals 1, we give it a little flick, it moves this way, right? So it gets to this point right here, x equals like 1.5 meters, and it's right there. The kinetic energy is 0, and as I said earlier, it doesn't stay there. Why doesn't it stay there? Because of that. So look, du dx is positive, agree? Positive slope, because this is the slope, but this is negative. So that means right here, there's a force that's negative. So if the particle is there, there's a force negative. So what does it do? It goes back. Okay, here, let's say the particle is right here. Again, the kinetic energy is 0, but here's a negative slope. Negative, negative is positive. That means there's a force that way. Okay? That's all there is to it. All right? Just like when you throw something up, when it gets to that turning point, glad I don't play baseball. When it gets to that turning point, what's the direction of the force? Down. Okay? So this is one of these useful formulas that we use once in a while. Okay, let's give you some practice. So this is the potential energy for a spring, 1/2 kx squared. This is the force law. Please use the force law. So in other words, use this equation with this u and come up with the equation for the force that the spring exerts on you when you push or pull it. So pause your video and do that real quick, please. All right, we're back. Okay, so u is 1/2 kx squared. So the force equals minus du dx. So that's minus d dx of 1/2 kx squared. All right, what's the derivative of x squared? It's 2x, right? So the derivative of x squared is 2x, so it kills the half. But we have a minus sign, so it's minus kx. Okay? Now, have you seen that before? Yeah, we have. When we talked about the Hooke's law, that's Hooke's law, right? F equals minus kx. So there you go, all right? So if you start here, you can get that. All right. So this is just a useful formula. All right. Now we want to talk about different kinds of forces, right? Different kinds of forces. So we want to talk about gravity. Gravity is a nice force. And what's nice? Well, you'll see in a minute. Okay, so gravity is a constant force, right? The force of gravity equals mg. It's constant, you know, when we're close to the surface of the Earth. So here's an object, and the question is, what is the work done by the Earth on this object as it falls a distance delta y? Okay, so now it's a constant force, so we don't have to do an integral. Isn't that nice? So work equals F dotted with delta y, right? Okay, so the gravitational force is down. Delta y is down, so the angle is 0, right? So the force is mg. Delta y is delta y. And the angle is 0, so we have cosine is 0. Cosine of 0 is 1. So the answer is just mg delta y. No kidding. All right? Okay, so that was nice, right? Such a straight, right? Okay. Now let's get a bit more complicated. Now let's say, instead of just dropping the thing so it goes straight, let's have it go down an inclined plane. Okay? So same question. What is the work that Earth does on the object when it moves a vertical distance, delta y? So that's not helpful. That picture is not helpful. Let's make it helpful. So let's say, let's do this, okay? So this is still the vertical distance, delta y. This is delta s, along the plane. Here's some angle, right? Okay, so this is this one. Okay, so, just do what we always do. So work is dotted with delta s, right? Because this is the displacement, delta s. So it's mg, or fg, sorry, dotted with delta s. So that's mg delta s cosine theta, right? Because that's what the dot product is, cosine theta. All right, now let me do something here. Okay, what is delta s cos theta? So what's delta s cos theta? It's delta y, right? Delta y. So delta s cos theta, this here is just delta y, right? Good old trigonometry. So the answer is the same as before, mg delta y. Same answer, okay? So what we see is that the work by the Earth on the object is the same as if we drop it or if it goes down an inclined plane. Same work. Okay, so now I want you to guess. So now we have this weird curve, right? Some curved ramp. It's not straight like the previous one, right? So just guess. So now we have the ball doing some weird thing, right? So what do you just guess? What do you suppose the answer is? I mean, mg delta y on that one, mg delta y on that one. Well, guess what? Same thing, mg delta y. Okay, and you can prove it, but I'm not going to. All right. So, all right. So you get the same thing. So here's the important thing. It doesn't matter which path the object takes. This path, this path, this path, this path. Who cares? It doesn't matter. The only thing that matters is the vertical height, delta y. Because for every single one of these situations, the work done by gravity is just mg delta y. Well, what does that mean? It means that gravity is a path-independent force, right? Because it doesn't depend on the path. It's independent of the path. So gravity is a path-independent force. And you'll see why that's wonderful. Okay, so there's not too many path-independent forces, by the way. And we'll get to that. Now, on the other hand, let's talk about friction. Let's talk about friction. So, the question is friction a path-independent force like gravity? Well, okay, here. We want to go from here to here. So we're looking down on a table, right? And we have a block, and we're moving it along the table. So we can move it, this way, just directly, right? From P to R, we can move it that way, or we can go this way and then that way. So the question is, what do you think? Do you think the work done by the frictional force is the same for this path, and then this path? What do you think? Do you think the work's going to be exactly the same? I mean, just think if there's sandpaper over the table and you have a block with sandpaper on it. Do you think the work is going to be exactly the same for this path and this path? No way, right? No way, okay? So gravity is not path independent, all right? Gravity, what did I just say? Friction, sorry. Friction is not path independent. Friction is path dependent because the work for this path is different from the work different than the work for this path, okay? So friction, all right, so let me get this right. Gravity is path independent. Friction is path dependent, okay? Path dependent. All right, so here's a silly question for you. So this is a pig. I don't know if you can see it. It's a greased pig, all right? Greased pig. What does that mean, no friction? A greased pig has a choice of 3 frictionless slides along which to slide to the ground. Rank the slides according to how much work the gravitational force does on the pig during the descent. And you rank greatest to least, okay? So pause your video and figure that out, please. Okay, what did we learn about gravity? Path independent, right? The work done by gravity is path independent. So what's the answer? All the same, right? Because it's path independent. Okay, one more. Wow, this is cool. This is pairs. Okay, what is the work done by the gravitational force on a passenger of mass m on a Ferris wheel of radius r making 1 complete revolution? So pause your video and figure it out. Okay, so 1 complete revolution. So let's just say here, here. So what's the delta y? 0. So what's the work done on the passenger? 0. What in the world is that? That's supposed to be a pi. Whatever. It's kind of funny. All right, let's quit.